Hey there, my name is Bruno O'Keefe, and this is Physics Lab 5. Like Lab 3, this is going to be an entirely coding-based lab, and in fact, I decided to base it off of one of the what-if questions from Lab 3, which was what if we had an orbital system, but in a more complex populated system, in which you have more than, the two bodies and your spaceship interacting. And so in this lab, I'm going to be looking at the physical and logistical differences between getting a stable orbit in the single moon system versus I decided to model another double moon system. As with all physics labs that we've done this semester, we're using the velocity update formula and the position update formula, which come from Newton's second law. Also from Newton's second law, we're taking from Fnet, splitting it into the parallel and perpendicular components of force, since we're dealing with circular motion. And then since this is also dealing with orbital mechanics, planetary systems, we have the calculating the force of universal gravitation. So in the code, our system and surrounding actually differs for what section of the code we're using. We choose a different system for calculating the forces on each of the moons and the spaceship respectively. So for each of those, we have to calculate the position vector between our system and the one element of the surrounding exerting gravitational force on it, and from there we can apply the universal gravitation formula for each of those individual forces, g times each of the masses times the unit vector over the magnitude of the vector squared. And when we sum all of those up, that's going to be the individual force on a given system. The initial conditions for the experiment were we had the spaceship on one of our two identical orbiting moons around the planet, and it was blasting off from zero velocity to try and enter a stable orbit. From there, it's just applying the velocity and position update formula for everything in our system except the planet, so that's both moons and the ship. And from there, it was just tinkering with the velocity of the ship to get it to some sort of stable orbit. So, as far as the differences between the single moon system and the double moon system, it was significantly harder to get it into any sort of stable orbit with the two moons, especially, one as kind of nice and symmetrical as we had in the single moon system, because there were just a lot more gravitational interactions going on. So, it would typically end up with either the ship crashing into one of the moons or getting like orbital slingshotted just completely at escape velocity out of the whole system. Even here, you see, there are like four separate orbits that it was in at different points, and including some close calls that you never really saw with the single moon system, just because there was so much more complexity in what it was dealing with. As far as possible sources of error, obviously this isn't the most realistic system. One of the biggest things is that we have the planet just stationary in the center, not being influenced by the gravity of anything else, and also the planet itself isn't orbiting a star. But one of the nice things about being able to model systems like this is that even though it would increase complexity in the observed reactions between them, as far as the physics and modeling it, at least computationally, we can just apply all of the same physics that I outlined earlier with, position velocity update, and then universal gravitation and calculating each of the forces. And that's one big difference between doing physics computationally versus analytically. Famously, the three-body problem in orbital mechanics, can't be solved analytically, but you can do it computationally in this manner. So off of that, the natural way to progress this is to have an even more populated system and trying to get a stable orbit with, moons, say, in concentric rings or an actual planet that's orbiting a sun or, star in the system. And obviously that would be much more difficult to have any sort of stable orbit there. But that's all for this lab. Thank you.